Imagine a world where your body is constantly talking to you, giving you real-time updates on your health long before you even feel a twinge. It's really not science fiction anymore. Today, we're doing a deep dive into something truly revolutionary. The cutting-edge fusion of artificial intelligence and wearable bioelectronics. This stuff is fundamentally redefining digital healthcare. Our mission is to unpack what these incredible devices are, how AI supercharges them, what they can actually do for our health right now, and, what challenges we still need to overcome for them to reach their full potential. For everyone. We're drawing our insights from a comprehensive review paper. It's called AI-Driven Wearable Bioelectronics in Digital Healthcare, and it was just published in the scientific journal Biosensors back in June 2025. It's a real deep dive into the very latest advancements in this, rapidly evolving field. So let's start at the beginning. We're talking about a fundamental shift in how we approach healthcare, moving from being reactive, only seeking help after symptoms appear.
Right. Waiting until something's wrong.
Yes, exactly.
Yeah.
To something truly proactive and personalized. So what exactly are these wearable bioelectronics?
Well, what's truly astonishing here is just how far these devices have actually come. At their core, wearable bioelectronics are a synergistic marvel, really. They rely on three integrated components. You've got the bioreceptor, which interacts with a specific target biomarker in your body. Then there's the transducer, which converts that interaction into a measurable signal, usually electrical. And finally, the processor unit, which interprets that data.
Okay, bioreceptor, transducer, processor. Got it.
Yeah. And think about it. Early glucose sensors, for example, they were relatively slow, kind of power hungry. Now we have devices using, say, synthetic molecularly imprinted polymers that can detect unbelievably tiny amounts of biomarkers almost instantly, right on your body.
Instantly.
Pretty much. With dissociation constants below 1 nanomolar, 90% specificity. And transducer sensitivity has improved maybe 1,000-fold. Processors went from needing the cloud, maybe 500 millisecond latency, down to under 20 milliseconds on the device, using tiny ML models, all while cutting power use from like 100 milliwatts down to under 5.
Wow. Okay, so less power, faster processing, way more sensitive.
Exactly. It's this collective innovation that's led to, well, the paper estimates a 10 to the 6-fold improvement in system efficiency since just 2010.
A million-fold leap. That's incredible.
It really is. And it's what makes continuous multi-analyte monitoring practical, with very low power budgets.
That kind of efficiency is game-changing. Does that mean we're basically solving the power challenge, or are there still big hurdles beyond just energy harvesting?
That's a great question. And yeah, we'll definitely circle back to power and its challenges. It's crucial. But first, let's look at the real-world forms these wearables take, because it's not just one thing. We're seeing several really exciting categories emerge. First up, biosensors. These are really key. They detect specific biomarkers like glucose, lactate, cortisol, electrolytes, often in sweat, saliva, or even the interstitial fluid just under your skin.
Right, the fluid between cells.
Exactly. So glucose biosensors, for instance, use enzymes like glucose oxidase.
Yeah.
They give real-time feedback for people managing diabetes. And their performance has just dramatically improved. We've gone from first-gen devices, maybe 2010, taking over 30 seconds for a reading.
Yeah, I remember those older ones.
To present-day sensors with sub-1 second response times. And the sensitivity is now in the picomolar to nanomolar range.
Okay, just to clarify again, picomolar to nanomolar sensitivity. What does that translate to for us? How small is that?
It means they can detect incredibly tiny amounts. Think, finding just a few specific molecules in an Olympic swimming pool. It's that level of precision.
Wow.
Okay.
Yeah.
And combine that with months of stability and AI helping sort out the signals. That's the enhanced selectivity. It means they're fast, they're reliable, and incredibly precise. Then you got the more familiar stuff, smartwatches and fitness trackers.
Right, like the one I'm wearing.
Exactly. They track heart rate using optical sensors, physical activity, sleep patterns, blood oxygen levels, SpO2. Some can even detect irregular heart rhythms, like AFib. Next are wearable patches. These are interesting. They're flexible, adhesive, pretty minimally invasive. They track vitals like ECG signals for your heart, body temperature, hydration levels by analyzing sweat. They're designed for comfortable long-term wear, days, even weeks sometimes. Moving to the real cutting edge, we have implantable devices.
Under the skin.
Yep. Things like pacemakers regulating heart rhythms, or neural stimulators for conditions like Parkinson's or epilepsy, and continuous glucose monitors, CGMs, which are often implanted just under the skin. They eliminate the need for those constant finger prick tests for diabetics.
That must be a huge relief for patients.
Absolutely.
Yeah.
But challenges here include biocompatibility, making sure the body accepts the device long-term, and again, power supply. How do you power something inside the body? Though people are working on innovations like harvesting energy from body heat or movement and wireless charging.
Oh.
And finally, smart textiles. This is cool. Biosensors woven directly into fabrics. Shirts, bras, socks.
Really?
In your clothes. Yeah, measuring things like cortisol levels from sweat, electrolytes, muscle activity. It offers seamless, totally unobtrusive health monitoring. The paper mentions an example, a wristband woven into the fabric that wirelessly analyzes potassium levels in your sweat.
It sounds like the materials themselves have to be, well, just as smart as the sensors, don't they? What makes these devices so adaptable and comfortable for everyday use?
Indeed, the materials are absolutely crucial. We're seeing huge advancements in flexible and stretchable materials. Things like polydimethylsiloxane, PDMS. It's a type of silicone you find in lots of medical devices and other advanced elastomers. They let the device conform to your body. And nanomaterials like graphene and carbon nanotubes, they provide excellent electrical conductivity, but still allow the devices to bend and twist naturally with your movement.
So they don't feel like you're wearing a circuit board.
Exactly. And for direct skin contact, biocompatible polymers, especially hydrogels, are used. They actually mimic some properties of human tissue, making them more comfortable. Plus, miniaturization and advanced encapsulation techniques are key. They protect sensitive electronics from sweat, humidity, mechanical stress, allowing for that continuous, unobtrusive wear.
Okay, and powering all this continuous monitoring, especially if they're tiny or even inside you, sounds like a really big challenge. How are they managing it without needing constant recharging?
Power management is definitely critical. It's a constant focus. Beyond just making batteries smaller or more flexible, researchers are really pushing energy harvesting. That means converting ambient energy from the environment or even your own body into electricity to power the device.
Like solar power, but smaller.
Sort of, yeah. Tiny photovoltaic cells can capture light energy. But also piezoelectric materials. They generate power from body movements, like walking or bending your arm. And thermoelectric materials, which use the temperature difference between your skin and the surrounding air.
That's clever, using your own body heat.
It is. We're also seeing flexible batteries, better wireless charging methods, and designing ultra-low power electronics. That includes using communication protocols like Bluetooth Low Energy BLE, which is designed specifically for very low power consumption, and near field communication, NFC, like for contactless payments.
Right, short range, low power.
Exactly.
Right.
Both enable efficient data transmission without draining the battery too quickly. However, is it increased connectivity, all these wireless protocols that make them so usable? Well, they also introduce a really significant challenge, one that maybe doesn't get enough attention sometimes. Security.
Ah, okay. The data itself.
Precisely. The very wireless nature opens up critical vulnerabilities. We need to think about eavesdropping risks, someone intercepting your health data. Data integrity threats, could someone tamper with the readings? And authentication challenges, especially if you have multiple devices talking to each other. How do they know they're talking to the right device?
That sounds concerning.
It is. And it's why strict compliance with regulations like GDPR in Europe and HIPAA in the US is absolutely vital. And the FDA's cybersecurity guidance, updated in 2023, provides a framework. It's all about protecting sensitive patient data. It has to be baked in from the start.
Okay, so we've got these incredibly sophisticated devices gathering tons of data, even powering themselves sometimes. But like you said, raw data, just numbers. By itself, it isn't particularly smart, is it? This is where the AI comes in, right? How does artificial intelligence take all this information and turn it into something genuinely actionable for us?
Exactly. AI, particularly machine learning and deep learning, is really the cornerstone here. It's the engine that transforms that raw sensor data into actionable insights. It enables advanced analytics, complex pattern recognition, and predictive modeling, often directly on the device itself. So, for instance, supervised learning is used a lot. This is where the AI learns from labeled data. It's used for classification tasks, like spotting arrhythmias in ECG signals. The paper mentions achieving 96% sensitivity.
So, correctly identifying almost all cases of arrhythmia.
Yes, exactly. And also for regression tasks, like predicting blood glucose levels based on current readings and trends. An algorithm type called random forests, that's a form of supervised learning, they're highly effective for real-time fall detection. They can achieve over 90% accuracy within just 100 milliseconds and operate under 5 milliwatts of power.
Wow.
Which makes them perfect for, say, monitoring systems for the elderly running right on the wearable.
That speed is incredible, especially for something critical like fall detection. So, Is that processing happening entirely on the little device itself, or is it still sending data off to the cloud for analysis?
That's an excellent point, and increasingly it's happening right there, which leads to this concept of integration of AI with edge computing.
Edge computing, meaning processing at the edge of the network, on the device.
Precisely. The AI processing happens directly on your wearable device, not primarily in some distant cloud server. This has huge advantages. It significantly reduces latency, the delay, down to under 100 milliseconds for critical alerts like that fall detection example, vital if speed
Makes
matters.
sense.
It also greatly enhances privacy because less sensitive raw data needs to be transmitted wirelessly. The insights can be generated locally.
Ah, that addresses some of the security concerns, too.
It helps, yes. And it drastically improves energy efficiency because you're not constantly transmitting large amounts of data. This enables potentially weeks-long operation on a single charge for some devices.
Uh-huh.
Plus, it makes the whole system more scalable. Less strain on cloud infrastructure if millions of people are using these devices. Beyond supervised learning, you also have unsupervised learning. This is used to discover hidden patterns in data without pre-existing labels. It's useful for things like clustering patients who might have similar health profiles or risk factors, even if we didn't know those groups existed beforehand. The paper mentions achieving high sensitivity and specificity here too, up to 98% and 93% respectively.
Finding patterns we didn't even know to look for.
Exactly. And then there's deep learning. This really excels at processing large, complex, high-dimensional data, like analyzing medical images, or data streams from multiple sensors at once. For example, 1D convolutional neural networks, 1D CNNs, are a type of deep learning specialized for sequential data, like heartbeats or blood flow signals.
Right.
They're pretty much standard now for analyzing raw ECG and PPG signals in smartwatches. They achieve really high arrhythmia detection sensitivity, 95–98%, while staying under that crucial 5 milliwatt power consumption limit. Even FDA-cleared medical devices are using these kinds of models now.
So they're medically validated.
Yes. And another type, recurrent neural networks, or RNNs, are good at interpreting sequential data over time, like continuous glucose readings, to predict future trends like where your glucose might be heading in the next hour. Sensitivity here is reported between 78–95%.
Okay, so AI isn't just looking at the data we have. It sounds like it's making it smarter, predicting things before they happen.
That's exactly right. It goes beyond just running algorithms. AI enhances the whole data processing and analysis pipeline. It can reduce noise and enhance the actual signal quality, which is crucial for getting accurate readings, especially when you're moving around.
Right, filtering out the junk.
Exactly. It performs feature extraction, pulling out the most meaningful bits of information, like calculating heart rate variability from a raw ECG signal. It drives pattern recognition to detect anomalies, subtle changes that might indicate the early signs of a disease. And, perhaps most powerfully, it enables predictive analytics, forecasting future health events, like anticipating a hypoglycemic episode for a diabetic patient, or estimating the near-term risk of a heart attack based on continuous monitoring.
That's empowering, giving you a chance to act before the crisis.
Precisely, empowering you to take proactive control of your health.
So bringing this all together, what does this mean for us, the listener, in our daily lives? What are the really practical applications of these intelligent wearables that are already making a difference or are just around the corner?
Well, the applications are truly transformative, especially in day-to-day health monitoring. We're talking about continuous monitoring of vital signs, but smarter. Real-time tracking of heart rate, yes, but also blood pressure variations, continuous glucose levels, blood oxygen, SpCO2, body temperature. You've got optical sensors in smartwatches for heart rate, wearable patches and cuffs, using AI to get better blood pressure readings for hypertension management, those CGMs continuously tracking glucose. The key is that this allows for much earlier detection of abnormalities, giving you timely alerts so you or your doctor can take action sooner. Then there's the detection of anomalies and providing early warning systems for chronic diseases. Wearables can reliably detect irregular heart rhythms like atrial fibrillation AFib, which is a major risk factor for stroke. Detecting it early can literally prevent strokes.
That alone is huge.
It really is. For diabetes, CGMs combined with those predictive AI analytics can forecast hypoglycemic or hyperglycemic episodes before they become dangerous, allowing for immediate intervention, like adjusting insulin or eating something. They can also monitor respiratory health, detecting subtle changes that might be early signs of conditions like COPD or sleep apnea.
Sleep apnea, right. That affects so many people and often goes undiagnosed.
Exactly. And importantly, we're seeing a big rise in wearable devices for mental health monitoring. This is a rapidly growing and I think really important area. Devices can monitor stress levels by looking at things like heart rate variability and skin conductance, how much you're sweating slightly.
And tell you when you're stressed.
Yeah, provide alerts, maybe even suggest interventions like guided breathing exercises through an app. They track sleep patterns in incredible detail, helping identify issues like insomnia or differentiating types of sleep apnea. Some research is even exploring using AI to analyze voice patterns, subtle changes in pitch or tone and activity levels from the sensors to assess emotional states. And some platforms are integrating this with real-time cognitive behavioral therapy techniques delivered via smartphone.
Wow, like a therapist on your wrist.
Kinda, yeah, providing support and tools in the moment.
That's incredible. The scope really is broadening from just physical to mental well-being. And how are these devices changing the bigger picture, the landscape of diagnosis, and even predicting how treatments might work out for someone?
Yeah, that's where it gets potentially even more impactful in the clinical setting. We're seeing AI-driven diagnostic tools for early detection of diseases emerge. Wearable ECG monitors, sometimes just patches or integrated into watches, can help detect cardiovascular issues like AFib, signs of heart failure, or even coronary artery disease indicators, often in real time or near real time.
So catching heart problems much earlier than a standard checkup might.
Potentially, yes. For neurological disorders, motion sensors combined with AI can analyze subtle changes in your gait, your walking pattern, or tremors. These can be early signs of Parkinson's or even Alzheimer's disease. Catching these conditions earlier allows for earlier intervention, which can potentially slow disease progression and improve quality of life.
Right. Early intervention is key for so many conditions.
Absolutely. They can also help detect early signs of infections by monitoring temperature and heart rate patterns, or, as we mentioned, conditions like sleep apnea. Then there's the predictive analytics for disease progression and patient outcomes. This is really powerful. AI models, fed with continuous data from wearables, can start to forecast the likelihood of complications in chronic diseases like diabetes or heart failure. They can predict post-surgical risks like infections or blood clots based on your recovery trajectory measured by the wearable, and even offer more personalized prognosis for complex conditions like cancer or heart disease based on how your body is responding to treatment moment by moment.
So tailoring treatment based on real-time feedback from the body itself.
Exactly. It empowers both patients and clinicians to make timely adjustments to treatment plans, hopefully improving long-term outcomes. And if we connect this to the bigger picture, the integration of wearable bioelectronics with electronic health records, EHRs, this is a potential game changer for the whole healthcare system.
Getting that data into the doctor's hands easily.
Right. Imagine your continuous wearable data seamlessly merging with your official EHR. It creates a much more comprehensive, dynamic, real-time patient profile. This enhances clinical decision-making, enables really robust remote patient monitoring, and telemedicine.
Especially important for rural areas or people with mobility issues.
Definitely. And it provides valuable aggregated, anonymized data for population health management spotting trends across large groups. We're seeing progress here. Interoperability breakthroughs, like the wider adoption of standards like FHIR, that stands for Fast Healthcare Interoperability Resources, it's a data standard.
Okay.
And platforms like Apple Health Kit and Google Fit are making this connection easier. The paper mentions successful pilot programs linking smartwatches directly to hospital EHRs for managing diabetes patients. And strategic partnerships are forming, like Fitbit working with Epic or Withings with Cerner, two major EHR providers to deploy more affordable, integrated solutions and improve accessibility.
Okay, this all sounds like a truly massive step forward, a paradigm shift, really, in how we manage health. But what are the big hurdles? What are the major roadblocks we need to overcome for these intelligent wearables to truly fulfill that potential and become, a standard part of healthcare globally?
You're absolutely right to ask that. There are significant challenges, and we need to be realistic about them. One huge area revolves around ethical and privacy concerns. Data security is paramount. We need robust encryption, secure data transmission protocols, basically making sure that sensitive personal health information is protected end to end.
From the sensor to the doctor and everywhere in between.
Exactly. And compliance with regulations like GDPR and HIPAA isn't just a suggestion, it's non-negotiable. Then there are the deeper ethical implications of AI making health-related decisions, particularly around algorithmic bias.
Bias. How so?
Well, if the AI models are primarily trained on data from one demographic group, they might not perform as accurately or fairly for other groups. This could lead to disparities in care.
Ah, okay, so the training data needs to be diverse and representative.
Crucial. And we need transparency in how these AI algorithms work so we can understand and trust their outputs. Lastly, under ethics, is ensuring informed consent and patient autonomy. Patients have to fully understand how their data is being collected, stored, used, potentially shared, and they must have meaningful control over that access.
So it's not just about building the tech securely, but also building trust and ensuring fairness and transparency in how it's actually used.
Precisely. And this ties directly into the next major challenge area, regulatory and legal issues. We need clear, consistently applied regulatory frameworks, like the FDA's pathway for medical devices and GDPR for data privacy. These need to keep pace with the technology. Standardization is also vital common standards for AI algorithms and the wearable technologies themselves. It helps ensure consistency, reliability, and interoperability between devices from different manufacturers and different healthcare systems.
So your data isn't locked into one company's ecosystem.
Ideally, yes. And then there's the really complex legal landscape around liability and accountability. If an AI-driven healthcare decision based on wearable data leads to a negative outcome, who's responsible? Is it the AI developer, the doctor who acted on the AI suggestion, the device manufacturer, the patient? These are thorny questions without easy answers yet. And finally, a very practical but huge hurdle, cost reduction and accessibility.
Yeah, this sounds expensive.
It can be. Making these advanced technologies affordable and accessible for everyone, not just the wealthy or tech-savvy, is critical if we want them to have a broad impact on public health. The paper notes some strategies. At the proof-of-concept stage, research labs are substituting expensive noble metal electrodes with cheaper carbon-based alternatives. This can cut material costs by over 90%.
So maybe performance isn't quite as good yet.
Sometimes they might need more sophisticated signal processing to maintain accuracy, that's true, but it's progress. For scaling up, manufacturing techniques like roll-to-roll printing, think printing electronics like newspapers can lead to significant, maybe 40–60% cost reductions compared to traditional batch processing. Modular device architectures also help achieve economies of scale. And looking at policy, the World Health Organization's Essential Diagnostics List provides a kind of framework. It helps prioritize good enough, affordable solutions over the absolute cutting-edge tech that might be unaffordable for many healthcare systems.
Finding the right balance between innovation and access.
Exactly. The paper gives the example of hearing aids. Their cost plummeted from around $4,000 to $400 in the U.S., partly due to FDA deregulation allowing over-the-counter sales. It shows how coordinated technical and regulatory strategies can dramatically impact affordability.
Okay, so significant challenges around ethics, regulation, and cost. But despite these hurdles, where do we see this all heading? What's the future vision? What gets you excited?
Oh, the future holds immense promise, absolutely. It's really driven by continuous advancements on multiple fronts. We'll definitely see further advancements in both AI and the wearable technologies themselves. AI models will become even more sophisticated, better predictive capabilities, catching anomalies even earlier, leading to more accurate diagnoses. Sensor technology will keep shrinking, becoming more power efficient, and monitoring an even wider range of physiological and biochemical metrics. Maybe even things like detailed neurological activity non-invasively.
Brain activity, wow.
It's being researched. And the integration with faster networks like 5G and the broader Internet of Things, IoT ecosystem, will allow for more seamless, truly real-time data transmission and analysis. Of course, bottlenecks remain. Ensuring training data is diverse, managing power consumption for even more complex sensors, dealing with signal drift over time, ongoing cybersecurity risks, and achieving truly universal interoperability standards. These are still active challenges. We'll also see a much bigger shift towards truly personalized and preventive healthcare. AI-driven wearables won't just give generic advice. They'll provide highly tailored insights and recommendations based on your individual patterns, your sleep, your diet, your activity, your unique physiology, transforming healthcare into a genuinely prevented, proactive endeavor for the individual.
Moving beyond treating sickness to actively maintaining wellness.
That's the goal. And AI can really help bridge the collaboration between patients and their providers. But we still need to address issues like data fragmentation across different apps and devices, ensuring people actually use the wearables consistently, those persistent privacy concerns, sometimes clinician skepticism about the data quality, and figuring out reimbursement models who pays for this. These are critical bottlenecks. There's also a very strong focus, necessarily, on enhancing affordability and accessibility. We'll see more scalable manufacturing innovations like that roll-to-roll printing becoming mainstream, and more use of low-cost, sustainable biomaterials, things like organic semiconductors or even cellulose-based substrates for sensors.
Making them cheaper and maybe greener too.
Potentially, yes. There's also a growing push for developing open-source ecosystems. Think modular hardware designs that anyone can build upon, and shared repositories of validated AI models. This could accelerate innovation and lower costs. And policy will play a huge role. We need accessibility frameworks, maybe tiered pricing models, public-private partnerships to ensure equitable access globally, not just in wealthy nations. And that brings us to the potential global impact. This is where it gets really exciting, I think. These technologies have a profound potential to address health disparities worldwide, particularly in low-resource settings where access to doctors and clinics is limited. Affordable, scalable solutions for remote monitoring could be revolutionary.
Bringing healthcare expertise to remote areas via technology.
Exactly. And global collaboration is absolutely essential to make this happen. The paper highlights initiatives like the IE and World Health Organization having a joint wearable bioelectronics working group, academic industry partnerships like one mentioned between MIT and the Broad Institute focused on flexible electronics, and healthcare provider networks like the Mayo Clinic working on integrating wearable data into actual clinical practice. This kind of cross-sector collaboration is what accelerates the translation of research breakthroughs into real-world clinical implementation that benefits patients.
This has been a fascinating deep dive. It really shows that this convergence of AI and wearable bioelectronics isn't just some passing trend. It feels like a genuinely groundbreaking shift. We really are moving from a healthcare system that largely reacts to illness toward one that anticipates, personalizes, and hopefully prevents.
Exactly. These technologies offer truly unprecedented opportunities for detecting diseases earlier than ever before, for managing chronic conditions much more effectively, and for developing truly precise, personalized therapeutics. But, as we've discussed quite a bit, realizing this vision isn't automatic. It requires sustained, interdisciplinary collaboration. We have to tackle those significant hurdles head-on, from ensuring data privacy and algorithmic fairness to, crucially, guaranteeing equitable access and affordability for everyone, everywhere.
It's clear the future of medicine is becoming fundamentally smarter and vastly more connected, and the potential to democratize healthcare access to improve outcomes on a truly global scale.
Yeah.
Well, it's immense. So thinking about all this, as these incredibly intelligent wearables become more and more integrated into our daily lives, perhaps even invisible, what role will you, the listener, play in shaping this future? How will this technology redefine what it even means to be healthy in the coming decades, especially considering the important policy frameworks being hammered out right now to try and ensure this powerful technology is adopted both equitably and responsibly?